Okay, so in chapter 6, we're going to talk about the normal distribution. Let me show you the page of the book that I'm looking at here. Of course, this is in MyMathLab, and you know how to go there. The way I went there again is once in MyMathLab, you go to Multimedia Library, and then I selected the chapter 6. Then scroll down to multimedia textbook, and let me show you again. This is multimedia textbooks, find now, and these are the list of the topics that we're going to be looking at in chapter 6. We're going to do the first 4 sections of this chapter, and of course if you click on the link, it will open chapter 6 page from the chapter 6 section 1. And they should be coming up pretty soon here. Now, as this thing is loading, let me also show you. This is where I'm going to be doing my work. Let me show you something here. Here's my OneNote. So there you have it. Chapter 6, the normal distribution. Again, 4 sections we're going to cover. In section 6.1, we're going to talk about the normally distributed random variables. And as we're looking for this, let me take a look at and see if the page of the book is up, and sure it is. Okay, so this is what we're going to be looking at. This is page 254 of your textbooks if you want to refer to the pages of the book. So I'm going to be going back and forth between the book and between my own notepad. So let me minimize this one, and here it goes. Now, before we actually look at the normal distribution, let's talk about a continuous random variable. A continuous random variable. Now, we already know about continuous variables. The only difference now is that we added the word random to it. So a continuous random variable, let's call this a random variable whose outcome or outcomes lie inside an interval. And we talked about numerous examples when we talked about continuous variables. So remember, one thing I mentioned was that anything that is measured, let me just put a note on that one. Note, all measured quantities, measured variables, let's call them. All measured variables are continuous. Okay. So examples of these we've talked about before would be things such as weight, height, time, for instance, and so on, etc. These are all measured quantities. Now, the probability distribution of a continuous random variable, it's also continuous. So, let me insert, let me go to home and actually get my eraser and erase this one, and let's do this. So the probability distribution of a continuous random variable is continuous. Now, the normal distribution is an example of such distribution. So let me shrink my view here. Okay. So now let's talk about the normal probability distribution. The normal probability distribution. This probability distribution, again, is continuous. And some of the properties of this distribution, let me first draw the distribution for you. So I'm just going to use this. Here's what this distribution looks like, and of course a better picture, we'll look at it in the book. The distribution, it's going going to look something like this. Okay, the random variable, we put the name of the random variable along the horizontal axis, so that would be like the x. That's our random variable, x. Now, this distribution is symmetric. The center of the distribution is where the mean is, so we're going to denote that with mu. And the deviation is roughly about where that is. This is where sigma is. Now, if you do a blow up of this segment of the curve, actually something interesting goes on in that area. And let me just kind of do a blow up of that segment right about here. Now, one of the measures of a curve, one of the characteristics, I should say, of a curve is its curvature, or they call it concavity. Now, the concavity or the curvature of the curve I've just drawn, it looks like it's facing down here, facing up here, and kind of where the two meet, right about would be here. I'm using a mouse, so because I think there is a highlight, yellow highlight that you can see. So right about there is where the up and down arrows come together. So this is roughly where the two meet, the up and the down arrow. Now this point actually has a fancy name. This point is called a point of inflection. And that's where the place, or that's the place where the curvature changes. Now, for the normal distribution, this point of inflection is exactly sigma units away from the mean. Okay, so that's pretty much what that is. Now, the curve actually has a mathematical function to it, which the formula is in the book. Let me just write this function for those that may be interested. I know maybe not too many are interested in the form of the function, but this is what this function looks like. Actually, let me do this. I want to delete this part and move it a little bit lower. Let me delete that one too. And oh, I know what I can do. There you go. I can just erase it this way. There you go. Okay, so I was going to write the form of the function. So here's what the form of the function looks like. For those again that are interested, f of x is equal to, let's see, it's going to equal to 1 over square root of 2 pi sigma times e to negative 1/2 parentheses x minus mu over sigma, and then quantity squared. So it's kind of convoluted formulas. Now some of these, what makes up this function, some of these letters you recognize. For example, e is approximately 2.718 and so on. Pi, I'm sure most of you are familiar with pi, is 3.14 mu is the mean, of course, and sigma is the standard deviation here. And what else? Okay, x here, by the way, x can be any real number, so x could be between negative infinity to infinity, and of course mu likewise is between negative infinity to infinity, and the deviation we take it to be positive. Now, let's see. So this is a probability distribution. That means the area under the curve must be 1. No, so that just reminded me of something here. For any continuous probability distribution, the area under the curve is synonymous with probabilities. So in other words, if you want to find probabilities under this curve, I need to be able to find the area under the curve. Now, the area under this curve, because it's not a well-defined shape, such as a triangle, rectangle, circle, and so on. So I don't have a formula for finding the area under the curve. So we have actually a couple of choices here. One way is we can use the table that's in the back of the book. The authors provided the table for us, which we will be looking at. And then the other is to use StatCrunch, the software that we've been using for the course. So I'll show you both how to do this. So first of all, let's take a look at some normal distributions, some curves. Let me go to the page of the book now and actually show you some of these normal distributions that's in your book. So for this one, let me go to that page. Now, some of the properties are listed here that you can see right in about here. Now, this distribution, they call it a density curve. The word density comes from physical sciences. The scientists, engineers, they refer to this as density, a rather technical term. And then I'll just bypass over that. Now, this function or the curve is a positive curve, so always sits above the x-axis. And as we mentioned, because this is a probability distribution, the total area under the curve has to be 1. Okay, now this curve, the one that I just drew, the curve, there you go. This curve that I have drawn, if you note here, the curve right about here, this curve goes indefinitely in the right direction to infinity, they say, and it goes indefinitely to the left, which would be negative infinity. And it does so without touching nor crossing the x-axis. So there's never a point of intersection. Now, we're not going to show the mathematics of how the area under this curve is going to become 1. So we're just going to accept that. And let me now go and actually show you some of these distributions that are in your book. So I'm going to go to the next page, and in the next page you're going to actually see a normal distribution. So there you go. This is what the normal distribution looks like right up here. This is the normal distribution that we're looking at. Now, there's not a single normal distribution, so depending on the mean and deviation, you have a different normal distribution. All normal distribution looks symmetric and what we call bell-shaped. Now, the bell shape, maybe the two-dimensional version, it's difficult to see the bell-shaped nature of this distribution, but let me kind of show you. If you look at the three-dimensional version of this distribution, the three-dimensional version may look something like this, and now you can kind of see more of a bell nature of this distribution. So there you go, and that would be however you label these. There you go, that would be a three-dimensional version of this distribution, which is called the bell-shaped distribution. So just want to clarify the terminology for you here. Okay, and then let me go back to the page of the book, and here you go. Now, every probability distribution has what we call parameters. The parameters are pieces of information that you need in order to describe the distribution or be able to use it, draw it, and find eventually the probabilities. Now, for the normal distribution, the parameters of the distribution are the mean and deviation. Okay, so let me write that over here for you. So we're going to say that parameters of normal distribution are mu and sigma. Now, this is how we usually write the normal distribution, n for normal, and then the value of the parameter mu and sigma, which define the distribution. So for example, let's say I have a normal distribution that has a mean of 100 and deviation of 5. So this is how we would be writing or addressing that distribution. Okay, so hopefully you're good with that piece of information. Now let me scroll down and go back to the page of the book. So here in this page, or in this drawing I should say, we're looking at 3 normal distributions. So this is actually one normal distribution right about here. This is a normal distribution. The center of this distribution is -2. This is a number line. What's below it is a number line. Here's 0, the reference point, and then it goes positive, to the left of that negative. So this is a normal distribution whose center is at -2 and deviation is 1. So if I look at like that point of inflection that I told you about, that's roughly is going to be 1 unit away. Let me, if I can get my drawing tool here and draw for you. Hold on. Sorry about this. Let me see. This thing is coming up, and okay. I'm sure you can see this. This is what I'm using to do my recording. And let me see. Okay, never mind. Sorry about that. There, we put it here. Okay, so anyhow, so you're looking at 3 different normal distributions here. This one in the middle, this distribution, this one is actually right here, this one. This one has a center as 3, deviation half. This one is a different center and location, 9, and deviation is 2. So because the mean defines the location of this distribution, we call the mean mu, the location parameter, and the deviation, which determines the shape, how narrow, how tall, or how wide and flat the distribution is. We call that the scale parameter. So here you're looking at, again, 3 different normal distributions. Now, if you notice, all of these pretty much taper rather quickly. This one, all of them. If you look at, for example, so many deviations above, so many deviations below, you cover the entire area under the distribution. So that's what this is. Now, I mentioned mu and sigma are called the parameter of the distribution, and we use them to label the distribution. So here's where you're looking at actually the name of this normal curve. You can see the nice symmetry of this distribution. The center of the distribution is mu, and you have 1 deviation, 2, 3 above, 1, 2, 3 below, and if you note, 6 sigma, 6 deviation, covers almost the entire curve. And that's why this curve is so useful, because it tapers quickly, and we're going to take advantage of the behavior of this curve later on when we talk about other topics. Now, so we're going to take a look at now a very special normal distribution, one that, let me go to page 258 actually here, page 258, enter. Okay, now on to page 58 here, we're going to look at a very special normal distribution. This is what we call the standard normal distribution, or normal curve, they call it. A normal curve in mathematics is a curve that looks like what you're seeing here. This is called a normal curve. It's a smooth curve. Continuous means there's no break, holes, gaps, jumps anywhere on the curve. And because of the shape, it's called a normal curve. So anyhow, this curve that you see is very special. Standard normal here, the word standard normal distribution, this one that we're looking at right here. This tells us the mean of this distribution is 0, as you see up here. Mean is 0 and deviation 1. So if the mean is 0, deviation 1, we're going to call that a standard normal distribution. Now, and usually the letter we use for that random variable is letter z, not x. So we're going to kind of reserve that for a standard normal distribution. So therefore, let me go back to my notepad, and we're going to do that. So we're going to call a standard normal distribution, therefore, standard normal distribution is going to be one that has mean 0, deviation 1. And they have to be exactly that, folks. If, for example, mean is 1, deviation 1, that's not going to work. And of course, mean 1 is okay, deviation cannot be 0 because right up here we said sigma has to be positive, remember? Right up here. This is when we said sigma must be positive. But anyhow, this is how it should be. Now, standard normal distribution, just like any normal distribution, again, it's symmetric, bell-shaped, so that's portion of the curve, and here's the other portion of that curve. The variable is z, so we're going to use z from now on for that. The center of this distribution is 0, and roughly the point of inflection is there, so that's going to be 1. Okay. Now, it turns out, by the way, let me show you this thing here. There you go. Okay. So it turns out that there's this process. This process is called standardization. What the standardization does is the following. It can take any non-standard normal distribution and transform it into a standard normal distribution, that is mean 0, deviation 1. So what you're seeing here in this sketch, in that figure 6.6, what we're seeing is this process of quote-unquote standardization. So here what the author's done, he's selected 3 different distributions. These are 3 different normal distributions, 3 different means, 3 different deviations. And he puts every one of these through this formula right up here, this formula, which is z equal x minus mu over sigma. And then he transforms, in effect, every one of these into what we call the standard normal distribution. So this is, again, it is a mathematical transformation, and to kind of show you the effect of what happens with this transformation is this. So we're going to call this standardization. Standardization. And this is the process by which a z is created by taking x minus mu divided it by sigma. So now here's how this process works. Let's say I have a normal distribution right there, and suppose this is x. And here's what my normal distribution looks like. It's highly peaked and symmetric. The center of distribution, let's say, is 100. That's my mu. And let's say sigma here is, looks rather high peaked, and I'm going to go 1/2. Okay, that's what that is. Here's a 0. And if I look at one score, let's say under this distribution, this one score, I have an x value that is 100 and looks like about 1 deviation. I'm going to go 100.5 maybe, or let me go, 100.5. So in other words, I chose a score that is exactly 1 deviation above, 100.5. Now, if we do x minus mu, the numerator of this transformation, if I do x minus mu, in effect, what's going to happen is the x minus mu will transfer this distribution to the other side, which is at 0. Now, let me erase this distribution, this thing for now, and let me delete that part. Actually, I want to just erase this whole thing if I could. There we go. Let me just erase it. There we go. So I'm just going to move that over here. So remember, z is equal to x minus mu over sigma. Now, I can move this distribution to the left. It's exact same distribution, and I'm doing literally a copy and paste it. In fact, let me see. Maybe I should do that. Let me erase this, what I just did here. There you go. Let me erase this part. So if I can, I would like to, there we go, copy and paste here. That's just portion of that curve. Never mind. So anyway, it's just a redraw of that distribution. So there you go. I'm going to redraw the distribution here. So this is, in fact, what x minus mu has done. Now, when we divide by sigma, the effect of dividing by sigma here is to scale this. So indeed, this is going to scale it now to where this looks like a standard normal distribution, which looks something like that. So there you have it. That's what this z equal x minus mu over sigma does. So this red distribution now, this is where x minus mu over sigma occurs, and that's now as z. So random variable at this point transforms into a z with mean of 0. So what happened to this observation? 100.5, if you track, that's your x. So the z that goes with that is 100.5 minus 100 divided by 0.5, which is your sigma. Remember, sigma is 1/2 over here. And if you do this, you get z equal 1. There you go. So that means that same score under the standard normal distribution is exactly 1 deviation above, and this is the z score corresponding to a value of random variable 100.5. So that's what that is. Okay, and so let me pause this for a moment, and I'll be right back with more stuff. Don't go away.